So basically, notch sensitivity factor is that. So normally when there is a presence of stress concentration, what we used to do? We used to find out K sigma, okay, which is given by maximum stress divided by nominal stress, correct? We used to find out K sigma if there is a presence of stress concentration in the component for various types of loading. Now, in practice, the effect of this K sigma, so we find out, say, K sigma to be equal to somewhere around 5.5. Okay, so when we find out K sigma to be 1.55, its actual effect will not be 1.55, but it will be slightly less than 1.55. Okay, so therefore the notch sensitivity will give you the degree to which this theoretical stress concentration factor will have effect on the component. So that is what is called as notch sensitivity. That is the K sigma, that is theoretical stress concentration factor that we find out will have lesser impact or effect on the component as against 1.5. That means when I use notch sensitivity factor Q, this K sigma will come down by some amount. So that value of KFT is what we have to use in our Soderberg relation. Okay, that is given by KFT ABC sigma A plus sigma ND into sigma endurance plus mean stress divided by yield stress is equal to 1 by factor of safety. Okay, so while finding out fatigue, okay, that is fatigue stress concentration factor, the effect of stress concentration factor will be less. Okay, so how much is less is found out by notch sensitivity factor. Okay, so therefore KFT is given by 1 plus Q into K sigma minus 1. So where Q is called notch sensitivity factor, which will give you the degree to which the effect of theoretical stress concentration is felt. Is that okay? Or is that? No, not. In cyclic loading, the effect of notch or fillet, is usually less than that predicted by the theoretical stress concentration factor. The theoretical stress concentration factor K sigma. Next line. Notch sensitivity may be defined as the degree to which the effect of stress concentration is actually reached. Full stop. In notch sensitivity, if notch sensitivity factor Q, if notch sensitivity factor Q, if notch sensitivity factor Q is used in cyclic loading, comma, then fatigue stress concentration factor KFT, then fatigue stress concentration factor KFT is given by KFT is equal to 1 plus Q of K sigma minus 1. K sigma minus 1. Okay. If not given, we can take Q is equal to, if not given, we can take Q to be equal to 0.9. And take Q to be equal to 0.9. Is that okay? Is that okay?
So this notch, where is it placed? On the exact place where the load is applied, or?
No. It is only a factor which will reduce the effect of theoretical stress concentration factor K sigma. That's it. Is that okay? That is, see, they have found out by experiments that the theoretical stress concentration factor, whatever that is found out, will have lesser effect as what we calculate here. Say suppose I calculate K sigma to be equal to 1.55. Maybe by taking D by D is equal to R by D is equal to, I would have found out K sigma to be 1.55. But actually, the 1.55 may not be present. Effectively, there may be 1.45 is the stress concentration factor that is reached in practice. So that is indicated by Q, that is notch sensitivity factor. How much sensitive is the notch? Is it exactly equal to 1.5? Whatever, I am just taking example of 1.55. Is it exactly 1.55 or it is less? Experimentally, they have found it to be lesser effective. So how much lesser is given by this Q, that is notch sensitivity factor Q. Is that okay?
So is there a notch on the beam that you're assuming or not, sir? Because it says notch sensitivity.
No, notch is nothing but a discontinuity. Discontinuity can be in the form of presence of a hole, notch, fillet, stepper shaft, and so on. For all these discontinuities, in general, they call it as notch. That's it.
Okay.
Got it?
Yes, sir.
Okay, fine. So please note down this. So this Q will give us the degree to which this theoretical stress concentration factor will have the effect on the component. That's all. Because they have found out that exactly 1.5 K sigma value, whatever we get, will not have that impact. It will be less than that. How much less is indicated by notch sensitivity factor. Is that okay? Fine. So far, in all the problems, we used to take KFT to be equal to 1. So from now on, whenever stress concentration factor is to be considered, we need to find out KFT. Okay. If they say use notch sensitivity factor, then find out K sigma, use Q value, then get the value of KFT, substitute in Soderberg relation, and get the required parameter. So the addition here is from the previous problem that we solved. Here we need to find out KFT. If Q is given, we need to find out a new value of KFT. Before KFT, we need to find out theoretical stress concentration factor. Okay, find theoretical stress concentration factor for a given problem based on the conditions. Then substitute in this equation, get KFT, substitute this value of KFT into Soderberg relation. Got my point now? Yeah?
Yes.
Could you understand?
Yes, sir.
Yeah, it is a combination of stress concentration factor chapter and design for fatigue strength. Got it now? Yeah, take up this problem. This was asked for 14 marks. A round bar, a round bar, a round bar stepped down, a round bar stepped down from 1.5D, stepped down from 1.5D, it is diameter 1.5D to D, to diameter D, has a fillet radius of 0.2D, 0.2D, 0.2D. Okay, the same 0.2D can be asked in a different way. Put it in brackets, 20% of smaller diameter. So instead of giving 0.2D as fillet radius, then we give you as 20% of smaller diameter D. Okay, now down within brackets 20% of smaller diameter. Close the bracket. 20% of smaller diameter, close the bracket, as shown in figure, as shown in figure. Full stop. It is subjected to a varying bending moment of, it is subjected to a varying bending moment of, 400 Newton meter, 400 Newton meter, 400 Newton meter to 600 Newton meter, 400 Newton meter to 600 Newton meter. Full stop. Full stop. The material has an ultimate strength of, the material has an ultimate strength of 540 megapascal, 540 megapascal, and an yield strength of, 400 megapascal, 400 megapascal, 400 megapascal. Full stop. Assuming an FOS of 1.5, assuming an FOS of 1.5, assuming an FOS of 1.5, design the bar. Design the bar. Figure need not be given in this question. Design the bar. Okay? Okay? One of you please read the problem.
A round bar stepped down from 1.5D to D has a fillet radius of 0.2D.
Yeah.
It's 20% of smaller diameter,
Yeah.
as shown in figure.
Okay.
It is subjected to a varying bending moment of 400 Newton meter to 600 Newton meter.
Yeah.
The material has an ultimate stress of 540 megapascal and a yield strength of 400 megapascal.
Okay.
Assuming an FOS of 1.5, design the bar.
Yeah. So there is a stepped shaft. Okay. There is a stepped bar, something like this. Please look at the board. Please look at the board. Okay. There is a stepped bar. Okay. There is a stepped bar which is stepped down from 1.5 to 1.5D, this is 1.5D to D, correct? This is D. And it says the fillet radius is 0.2D. This is 0.2D is the fillet radius. Is subjected to a bending moment of. So this is bending moment of. Okay, that is bending moment I write it as MB. Bending moment of 400 Newton meter to 600 Newton meter. So you have got M max is equal to 600 into 10 power 3 Newton millimeter. And then M minimum is how much? M minimum is 400 Newton meter. That is 400 into 10 power 3 Newton millimeter. Material has an ultimate strength of 540 megapascal and a yield strength of how much? What is the yield strength given in the problem? 400 megapascal, correct? 400 megapascal, and use a factor of safety. N is equal to how much? It is 1.5. We need to design the bar. That is, we need to find the diameter of the bar. Okay, so here you have got maximum bending moment and minimum bending moment being given in the problem. Now, what we need to do? So we are not given with ABC values also. We have Soderberg relation here given by this expression. Since he has given you to find out stress concentration factor also. Okay, so we have to find out, since he has not given you to take not sensitivity factor. So we will not consider Q here, but we need to find out the value of KFT to be substituted in the equation of Soderberg's. So how do we do that? This is a stepped shaft subjected to bending moment. So go to which figure? Go to the stress concentration charts. If you have got with you, go to
2.25.
Yeah.
Page 40. 2.25 page 43.
2.25 page number 43. That's exactly correct. So find out D by D. D by D is 1.5D by D. So D and D gets cancelled. So we get 1.5. What is R by D here? R is 0.2D by D. D and D gets cancelled. We get 0.2. So therefore, the K sigma value is equal to how much? Go to figure 2.25. Okay. Find out for a D by D of 1.5, R by D of 0.2, what is the value of K sigma? Someone please give me the value of K sigma.
1.43.
1.43 exactly is what I have taken. 1.43, that is equal to KFT. Because why I have not considered Q is, in the problem he has not asked us to consider notch sensitivity factor. So therefore, we take K sigma to be equal to KFT. Okay. Now we have found out KFT value. Now we have to find out the mean stress and stress amplitude. Okay. So it is as usual. Sigma max is equal to M max divided by section modulus Z. That is M max is how much? 600 into 10 power 3 divided by section modulus. Then sigma minimum is equal to M minimum divided by section modulus, that is 400 into 10 power 3 divided by Z. So once we get that, I can find out mean stress is equal to sigma max plus sigma minimum by 2, that is 600 plus 400 is 1000 divided by 2 is 500, correct? 500 into 10 power 3 divided by Z will give me the mean stress, and stress amplitude is sigma max minus sigma minimum by 2, that is 600 minus 400 by 2, that is amplitude is equal to 200 by 2 is 100 into 10 power 3 divided by section modulus. Okay, right. So I found out mean stress, stress amplitude, KFT. And the value of ABC is what we need to take for bending. What is the value of A we need to take? Capital A is equal to, for bending, what is the value that we have taken in the beginning?
1, sir.
For bending it's 1, is it?
Yes, sir.
Yeah.
Yes, sir.
B is equal to 0.85 and C is equal to 0.8.
0.8.
Okay, so I have found out mean stress amplitude, KFT, ABC are known, only unknown now is sigma endurance strength. Okay, so sigma endurance, what we have decided yesterday, sigma endurance to be equal to 0.5 times sigma u, correct? So therefore, it is going to be equal to 540 divided by 2, that is 250 plus 20, that is 270 megapascal is the endurance strength. Okay, endurance strength is 270 megapascal. Substitute in the equation of Soderberg and find the diameter of the shaft. Okay, are you there with me?
So why did you
Why
equate
did you
K
ignore
sigma?
Q?
Yeah,
Okay.
yeah.
K sigma, why did you take it equal to KFT, sir?
Because in the problem, he has not asked us to consider notch sensitivity factor. It so happens in some problems, they will give you the notch sensitivity factor value also. Or sometimes they'll ask consider notch sensitivity factor. Then that time, if value of Q is not given, then we take it as 0.9. Otherwise, we just ignore it and take K sigma to be equal to KFT for classroom design. Is it okay?
Okay, sir.
Yeah. Please get me the value of diameter now.
$31.175.
How much? 31.17.
31.175.
B is equal to 31.17, that is 32. Others, please note down. In your laptops, is the writing clear for you? Is it quite clear, Tarun? In my,
Yes, sir.
Yes, sir.
the clarity is there because when I see in my laptop, no, sometimes it may be slightly blurred. In your case,
That's the net connectivity, sir. If the net connectivity is low, it will blur.
okay. Or should I increase the brightness of my laptop? Something like that?
No, sir. The clarity is based on the net connectivity, sir.
Okay. Yeah, others, please note down. Those who have not done, please note down the solution. Please note down the solution. These are all important problems. Any doubt, anybody in this? It's very simple. Basic equation is bending stress is bending moment divided by section modulus. Once you know that, things will be very easy. So mean stress, you find out max and minimum, mean stress you find out, amplitude you find out, and then get the value. Yeah, take the next problem. Anybody needing time?
1 minute, sir.
Yeah. Okay. Yeah, we'll take up the next problem. The stepper shaft with reduction ratio of 1.2. The stepper shaft with a reduction ratio of 1.2 the stepper shaft with a reduction ratio of 1.2 is to have a fillet radius 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 of 10% of smaller diameter of 10% of smaller diameter 10% of smaller diameter. Full stop. This shaft is to be made of material that has a notch sensitivity factor made of a material that has a notch sensitivity factor of 0.925 and shear stress of 160 megapascal shear stress of 160 megapascal at yield shear stress of 160 megapascal at yield and a shear stress of 120 megapascal and a shear stress of 120 megapascal at endurance limit. Full stop. The surface of component would have a surface of component would have a surface factor of 0.95 and size factor is 0.85 Full stop. Determine the diameter of the stepper shaft to sustain a twisting moment that fluctuates between 800 Newton meter and minus 500 Newton meter Okay, are you there? Someone please read the problem.
The stepper shaft with a reduction ratio of 1.2 is to have a fillet radius of 10% of the smaller dia.
Yeah.
The shaft is made of material that has a north sensitivity factor of 0.925 and
Yeah.
shear stress of 160 megapascals at yield and
Okay.
shear stress of 120 megapascal at endurance limit.
Yeah.
The surface of component would have the surface factor of 0.95,
Yeah.
size factor is 0.85.
Yeah.
Determine diameter of stepped shaft to sustain a twisting moment that fluctuates between 800 Newton meters and minus 500 Newton meters.
Okay. So now the stepper shaft is subjected to torsion. That much is clear, right? So we have a stepper shaft. I'll write the stepper. Please look at the board. Don't do anything. Okay. This is a stepper shaft. This is subjected to a twisting moment. Okay. And the ratio of stepper shaft is 1.2. That is, this is 1.2. Major diameter is 1.2. Smaller diameter is D. And the fillet radius is 10% of smaller diameter. That is 0.1 D. This is what is given. And he says notch sensitivity factor to be equal to Q is equal to 0.925 and the shear stress of 160 megapascal at yield, that is tau yield is equal to 160 megapascal and tau endurance is how much? It is 120 megapascal. Okay, and what else is given? The surface of component will have surface factor, that is the value of C is equal to 0.95 and the value of size is 0.85. B is equal to 0.85. Since he is worried about only B and C, so we take A to be equal to unity. Okay, and it has to sustain a twisting moment, that is T max is equal to 800 into 10 power 3 Newton millimeter and T minimum is equal to minus 500 into 10 power 3 Newton millimeter. We need to find out what? We need to find out the value of diameter D of the shaft. Is it okay? Is it okay? Anybody?
A value, will it be 0.6, sir? Because it's given.
Yes, sir. Since it's
No,
torsion.
that is what I told in the very beginning when we started with design for fatigue strength. If suppose it does not give you any value of A, B, C, then we take those values that we took initially. All right. Sometimes what will happen is you will be interested only in factors, like he has given you the value of B and C. So in such case, he is not interested in value of A. So therefore, we just neglect the value of A by taking it as unity. Suppose if it does not give any value of A, B, C, then we are going to take accordingly whatever that we initially assumed. If you look at here, the value normally we take is 0.85. But here he is having a very good finish of the surface. So therefore, he has given you to take it as 0.95. That means he is asking us to neglect the effect of load factor A. Got the clarity now? Why when we take ABC and when we assume the values of ABC? Could you get it now?
Yes, sir.
Yeah. So it is subjected to twisting moment of 800 maximum and minus 500 minimum. Correct? And tau yield is given, tau endurance is given. The suitable relation for shear stress is given by KFT, that is KF tau into stress amplitude divided by, that is tau amplitude, shear stress, no, tau A by ABC, tau endurance, okay, plus tau mean divided by tau yield is equal to 1 by factor of safety. Wherever we had stress amplitude, normal stress amplitude, we take it as shear stress amplitude, shear endurance, mean shear, yield shear. The another unknown we have is factor of safety, as not given you in the problem. So assume factor of safety n is equal to 2.5, because we cannot, with one equation and two unknowns, we cannot get the solution. So therefore, I'm going to assume factor of safety to be equal to 2.5. Okay. Now my job is to find out stress mean, tau mean and tau amplitude. So I need to find out tau max and tau minimum. So tau is given by T max, tau max is given by T max by polar section modulus, ZP. So what is ZP? Otherwise, what we normally used to take? 16T by pi d cube, correct? So Z will be equal to here pi d cube by 16. Whereas Z for bending is pi d cube by what? Pi d cube by
32.
32. So for torsion, it is going to be pi d cube by 16 is nothing but section modulus. So we can keep ZP as it is for because it will be easy for solving the problem or simplification. Now you can also take it as 16 T max by pi d cube and solve. Keep things in terms of D. That also can be done. So what is tau max here now? T max is 800 into 10 power 3 Newton millimeter divided by polar section modulus ZP. Then tau minimum is equal to T minimum divided by polar section modulus. This is minus 500 into 10 power 3 divided by polar section modulus. So once I do that, I can get the value of mean and amplitude, correct? So what is mean there? So tau mean is how much? Tau mean will be tau max plus tau minimum by 2. That is 800 minus 500 is 300 divided by 2. That is 150 into 10 power 3 divided by section modulus. Tau amplitude will be tau max plus tau minimum. I mean tau max minus tau minimum, correct? Divided by 2. Minus of minus is going to be plus. So 8 plus 5 is 13. So 13 divided by 2 is how much? How much? 1300 divided by 2 is how much? How much? I want answer. Is that correct?
Yes, sir.
650 into 10 power 3 by section modulus, tau mean and tau amplitude. Now I got. Now I need to find out fatigue stress concentration factor. So again, go to D by D. D by D is how much here? Is 1.2. 1.2 D by D. That is equal to 1.2. R by D is 0.1 D by D. That is equal to 0.1. So therefore, what is K sigma here? Or K tau? We can take it as K tau. Give me the value of K tau. Now we use Q value now. Give me the value of K tau.
So the line for D by D is
1.37.
1.2.
RCB.
Yeah?
The 1.2 line is not there.
Yeah, it's not there. You take in between, imagine a curve in between, and then get the value of K sigma.
1.36 in that case.
You are taking 1.36. I have taken it to be 1.34. What is the figure number, Tarun?
So 2.17.
2.17. Others, please look into.
It's 2.27. 2.27, sir. Step the shaft in
1.35.
torsion.
1 second. I'll check.
So you
You
don't
put
have the
2.27, correct? 2.27, page number 44. 1.34, 1.35, okay, that's fine. So it is 1.34 is what I have taken, okay. So now I have got not sensitivity factor to be considered over here. So therefore, my K of tau will be 1 plus Q into K tau minus 1, that is equal to 1 plus 0.925 into K tau is 1.34 minus 1. What will be the value of KFT now? Give me this value of KFT. 1 plus 0.92 into 1.34 minus 1. What is the value of KFT? How much?
1.3145.
0.314.
1.3145. Yeah, one observation you need to do here is Kf tau is 1.3145, whereas K tau was 1.34. This is what this Q, notch sensitivity factor, is all about. It will reduce the effect of theoretical stress concentration factor. That means it will give you the degree to which the theoretical stress concentration factor will have the effect on the component. That means if you see here, 1.34 is reduced to 1.31. Okay, that is what is notch sensitivity factor concept is all about. The effect of stress concentration factor will be reduced because of notch sensitivity factor, or notch sensitivity factor will give you the degree to which theoretical stress concentration factor will have actual effect. Is that okay? Is that fine? Right. So I have found out Kf tau, I have found out tau mean, tau amplitude. Factor of safety we have assumed it to be 2.5. Yield shear is given and enduring shear is given. ABC values are given. Substitute and get me the diameter of the shaft. Get me the diameter of the shaft now. Anybody? Any doubt in this? The ZP is nothing but 5d cubed by 16.
RCB.
Yeah, what is the diameter? So instead of writing it as 16t by pi d cube, I have written it as t by polar section.
50 mm.
Yeah?
Is it 50 mm, sir?
Yeah, exactly. That is 49.89, no? Mundio?
I got
49.89.
49.89.
Yeah. 49.8 rounded off to 50 mm. That's the answer, 50 mm. Others, please note down. Please note down, substitute, calculate. And one more important thing is, in the test, show all the equations, substitutions, and answers properly. Okay? All of you are there?
Yes, sir.
Sir,
Yes, sir.
the value, sir.
1 second.